So we're going to get started today, and what we're going to be doing is reviewing our single and double replacement reactions that we talked about last week, and learning about two new kinds of reactions: synthesis reactions and decomposition. So the synthesis reaction and decomposition reaction lesson isn't until January, so we're going to do it today. And over the break you could do it, or on January 2nd when you come back. But it's not too complicated. I think single and double replacement reactions are harder, in my opinion, than synthesis and decomposition, at least to recognize. So let's see here. Our objectives today are going to be review double and single replacement reactions, and then we're going to preview synthesis and decomposition reactions. And I say preview because you will probably need to go back into the lesson in Canvas and do some more practice, right? Because again, a lot of this reaction stuff, the more you do it, the more you're going to see the patterns, you're going to start recognizing what to do, and you're going to find it a lot easier. It's kind of like math. The more you do it, the easier it will be. So I thought a good idea for you guys to keep all this stuff organized is to create a chart in your notes. So I'm going to give you some time to do that right now. If you do your notes online, you could create a table like this. If you do them on paper, I would just create a chart on a whole piece of paper. And for the reactions that we know about so far, such as single and double replacement, see if you can fill in a description and an example. So I'm going to give you guys about 5 minutes to do that. And when you're looking for examples, feel free to go back in your notes, go back into Canvas if you need to. And if you finished this, if you want to just pop a 1 in the chat so I can kind of keep track of how much time we need to spend on this. Okay, we got 3 ones. We'll wait for a couple more here. Okay, so we got most people giving a 1 here. So we'll go ahead and go over this. So as we learn about these other reactions, you're going to go back to this chart and fill it in, right? This is just a really good way to review and sort of keep track of the differences between these reactions. A lot of times it's not hard to tell what the reaction is when you can see the whole reaction, but predicting the products can get pretty complicated depending on which one we are doing. So let's start with a single replacement reaction. What would we write? What did you guys write for a description of that? One element replaces a similar element in a compound. That's an excellent description. I took it a tiny bit further and said a metal or halogen replaces or switches places with another metal or halogen in a compound. But what Janie May said is 100% correct, and is a great simplistic way to say it. So one element replaces another element in a compound. Sounds simple, right? It really isn't as simple as we'd like. I would also make a note as well that you do need to use the activity series for these, right? That's a tool that you need to use in order to get these questions correct. So I would make sure that you know that and you know what that is. If you don't and you're new to the class, you will know what it is soon. And then what's an example of a single replacement reaction that we could put over here just to show kind of how this works? If you have your notes from last time, you should have a bunch of examples of single replacement reactions. All right, we'll wait for an example, but at the same time, if you don't know an example, but maybe you know a description for a double replacement reaction, if you want to go ahead and pop a possibility for that into the chat, or an example of a single replacement reaction. Again, feel free to use your notes. Feel free to Google looking for an example that would represent this. Okay, Janie May holding us down with an example. Thank you, Janie May. A great example. So we'll just pop that in here. A really great example here, sodium, and we have a copper sulfate, right? The sodium and the copper switch places. Now, again, we would refer to our activity series in order to know exactly whether that reaction would happen. We're going to review that in a moment. Otherwise, do we have anybody giving us a suggestion for double replacement that's not Janie Mae? I know you know what it is, Janie Mae, but let's see if someone else can provide us with an answer here. Thinking about that it's a double replacement instead of single replacement might give us a kind of a hint here. I'll start it out for you guys. Two ions switch places. Okay, so two ions switch places, right? In a single replacement, we have one thing switching. In a double replacement, we have two things switching places. So when we see single replacement, we always see one element by itself, and it's always a metal or a halogen, right? So metals being sodium, lithium, magnesium, etc. Halogens being fluorine, iodine, chlorine, etc. So keep in mind the double replacement is going to look slightly different than our single replacement reaction. An example of one that we did last week oh, whoops. I wrote the answer. I wrote this backwards. Sorry, guys. Okay, so here's an example of a single replacement reaction, or excuse me, double replacement reaction that we talked about last week, where we have a calcium chloride and we have a potassium carbonate. The calcium and the potassium switch places so that we get calcium carbonate and potassium chloride in the end. So this one, again, when you're looking at an equation, you should be able to say, okay, those two things switched places, and that's how you would know that that had happened. Versus the single replacement, there's something by itself switching places. Okay, so make sure you have that stuff written down, and as we do synthesis and decomposition today, we're actually going to come back at the end of this and see if we can't fill in the description and example for synthesis and decomposition. So be on the lookout as we go through. We're also going to review really quickly how to do these single replacement reactions with the activity series. So I'm going to give you guys, again, a couple minutes here to try to finish these reactions using the activity series. If this is something that's new to you, I suggest you go into the lesson right now in Canvas and spend a couple minutes looking at the lesson. This is something that we did last week, and there is a video about it. So I'm going to give you guys 2 minutes, and I'm also going to do this. So I'm going to cover my camera really quick. That didn't work. There we go. So I'm also going to be writing and working on this for 2 minutes. If you're not sure how to solve these, then spend your time right now writing out the first part of the reactions so that you can fill in as we go over. All right, so we're going to start going over this. Now I picked these two specifically because these are halogen single replacement reactions. Last week we mostly looked at metals. So there are halogens on the activity series. Chlorine is the most reactive and iodine is the least reactive, right? So that's important to note here because we see that iodine is by itself. That means that we need the iodine to be more reactive than whatever it's replacing. Well, guess what? Is iodine going to replace chlorine? See a lot of stares. What do you guys think? Is iodine active enough to replace the chlorine? Thank you, Janie Mae. No. So in this case, we would actually get no reaction, right? Iodine is lower on the activity series than chlorine. That means iodine does not react enough to replace the bond between sodium and chloride. If chlorine was over here, right, if we had the opposite situation where we had NaI plus chlorine, right, then we would actually end up getting a reaction. So again, this is one of those ones that could happen one direction but not the other. So iodine will never replace chlorine, but chlorine can replace iodine. Okay, what about the second equation here? We have lithium bromide and fluorine. So again, we come over here. Is fluorine more reactive than bromine? The answer is yes, right? Fluorine will replace bromine because it's higher up on the activity series. So that tells us this reaction will happen. So then we just have to switch. So do our lithium with our fluorine plus bromine will now be by itself. And then of course we would want to balance this entire equation. Right, we've got 2 fluorines on this side, so we need 2 on this side. We have 2 bromines on this side and 2 lithiums, so we also need, oops, why is this text box so big? We also need 2 lithium bromides, right? And we didn't balance this equation, but we just balance that one, it's fine. So this reaction would happen, right? Again, because looking at the halogens, fluorine is more reactive than bromine. Okay. So that was a review from last time. However, if you were not in the last virtual session or you're new to the class, this might be confusing. Go watch that session again, right? Because we do many examples of this, and we do a lot of examples with metals. Okay, so now we're going to learn about the 2 new reactions, synthesis and decomposition. They are exactly as their names suggest, right? Synthesis reactions, what does synthesis mean? It means to make or build. So what do? We take 2 separate molecules and we make a new compound. So you'll always see this kind of structure, an A and a B, and then in the new form we see an A, B together. So these are pretty easy to see because if you have 2 separate reactants and 1 product, it's pretty clearly a synthesis reaction. Now here's where it gets tricky. There's a lot of examples of how this could happen. I would suggest writing these down because these are going to give you the pattern for how reactions work. If you have a metal and a nonmetal, sodium's a metal, oxygen is a nonmetal, they form together. Okay. If you have 2 nonmetals, they can form a new compound. If you have a metal oxide and water, so these last 2 are the most confusing A metal plus a nonmetal and two nonmetals looks pretty obvious. You literally take sodium and oxygen and figure out their bonding. You take sulfur and oxygen and you figure out their bonding, right? So those two are easy. When we have a metal oxide, meaning calcium with an oxygen, some kind of metal plus an oxygen plus water, right? Then we get a metal hydroxide, where we end up having OH attached to our metal. So this one's a little bit tricky, right? Because it's not as simple as just adding all the stuff together. Same thing with the nonmetal oxide. Sulfur is not a metal. It's an oxide because it has an oxygen with it. When we add water to it, we end up getting an acid. So, and actually this is a base, which is interesting. So when we do metal oxide plus water, we get a metal hydroxide or a base. When we add our non-metal oxide with water, we end up getting an acid or an H in front. Right, so anytime you see an H in front like this, that means it's an acid. When you see an OH attached to something, that means it's a base. So those two are a little bit more complicated because, right, it's not as easy as just shoving everything together. You have to think about it. Okay, this one would become an acid, this one would become a base. The only difference being metal versus non-metal. All right, give me a 1 in the chat if you feel like, okay, I got this. This doesn't seem too hard. Ready to move on. Give me a 2 if you're like, can you say all that again? Or some of that again. All right, Michael, what part would you like me to say again? The metal oxide water and non-metal oxide water? If you are clear on this, right, take a second now to go back to your chart that you made in the warm-up. Metal plus non-metal. Okay, give me 1 second, Michael. Go back to your chart and write a description for what a synthesis reaction is and pick an example to put in there. You might want to put all of your examples, that's fine. So for a metal plus a non-metal, all we do is figure out the bonding. So in this case, right, oxygen needs 2 valence electrons and sodium only has 1 valence electron. So we're going to get 2 sodiums for every oxygen bonding together. And then they just have these 2s and 4s here to balance out the equation. So all you do when you add a metal and a non-metal is just figure out the bonding of that metal plus the non-metal together. Same thing with 2 non-metals. Sulfur and oxygen bonding together. Sulfur and oxygen have the same valence electrons, which is why it's a little confusing, right? But essentially, if you have 2 oxygens, then you have a need for 1, 2, 3, 4 valence electrons, and sulfur can provide those and double bonds. That one's pretty complex. But regardless, you just figure out the bonding on those. And again, if you struggle with that, right, you can always Google this to check, right? But make sure you understand the concept behind it before you start Googling stuff. Okay. So hopefully you guys wrote something about what synthesis is and one example at least, if not all 4 of these. So then a decomposition reaction is the complete opposite. Decompose, right, means to break down. So in this case, we start with 1 large compound and we break it down into an A and a B. It's literally the opposite. Now, we see 1, 2, 3, 4, 5 different options here. Again, this is all about recognizing the pattern. So I would write these down. I'll give you a minute or so here to write before I start talking. But as you're writing, see if you can kind of figure out what the pattern is or what's going on. Okay, so I went through and kind of added my thoughts on the patterns here. But there's 5 basic types. Our first one is the easiest, binary compound, where we have some kind of compound and it just breaks apart into 2 separate elements. Sometimes these can be ions, depending. Then we have our metal carbonate. This one is kind of new seeming, right? We have a metal and then a carbonate. Remember those polyatomic ions, right? Super, super important to have those listed somewhere in your notes. Carbonate is one of them. So is chlorate, right? So is hydroxide, I believe. So make sure you know that those are, CO3 is always carbonate. So when we have a metal carbonate, we end up breaking into a metal oxide plus carbon dioxide, right? CO2. Metal chlorate, we have a metal plus a chlorate. We end up getting a metal chloride plus an oxygen. Metal hydroxide, we have metal, we have hydroxide. Guess what? This is the opposite of the reaction we saw for synthesis. So we end up getting a metal oxide plus water. So this is literally the direct opposite of our synthesis reaction example. Same with an oxyacid, which is an oxygen-containing acid, right? We get a non-metal oxide and water when we break apart that acid. So those 2 are direct opposites of synthesis reactions. And I don't think this carbonate one is. I don't want to go to the previous slide, but I don't remember seeing CO2 anywhere. So yeah, that one's new. So metal carbonate and metal chlorate are newer ones, right? And the binary one is the simplest. So what we're going to do is we're actually going to try to predict reactions from this. And that's where this is going to come into play. These are our examples, our models. So hopefully the reactions that we look at to predict, we're going to have a similar setup either of a synthesis or a decomposition reaction, and we can figure out what the products would be. So that's why I'm writing out what these things are, right? So that we can think about what they would become when we predict a reaction. All right, again, give me a 1 if you're ready to move on. Give me a 2 if you either need more time or you have a question. And if you have a question, please just write what it is too. Okay, we got mostly 1s. Okay, good. And like I said before, this is kind of like math. It's a pattern. It's going to take time to sort of build awareness of that pattern. So if at first you're like, I have no idea what I'm doing, right? That's why we have these notes to go back to and use them as a model. So let's practice. We're going to try to predict the products of these reactions. So we're going to do the first 2 together, and then you guys are going to try to do the second 2 by yourselves. So the first thing we want to ask ourselves, is this going to be a synthesis reaction or a decomposition reaction? Or, to make it even harder, could it be a single replacement reaction? What do you guys think? Synthesis, decomposition, or single replacement? Sebastian gives a very brave no with a question mark. You were correct. It's definitely not single replacement because we don't have a halogen or a metal here. So that rules that out. Synthesis, I would agree. We have 2 things. We're probably going to be making something out of them. So then now we need to figure out, well, what do we have? To me, it looks like we have a non-metal plus a non-metal, right? We have a nitrogen and a hydrogen. So if we go back to our notes, oops, and we have 2 non-metals, all we have to do is figure out how they bond. So if we have a hydrogen and a nitrogen, do you guys know what our bonding situation between hydrogen and nitrogen would be? We'll think about our valence electrons as well. Nitrogen, I believe, has 5, right? We can always refer to our periodic table here. So, yep, nitrogen has 5 valence electrons, hydrogen has 1. So how many hydrogens do we need to go with 1 nitrogen to get 8? 3. So we're going to end up getting NH3, right? The 3 is the subscript here of the hydrogen. So that tells us we have 1 nitrogen, 3 hydrogens. Okay, now we need to balance our equation, which gets a little harder, right? It looks like we could put a 2 in front and be good. Right, because then we have 2 nitrogens, we have 6 hydrogens on that side, that would give us 6 hydrogens. Okay. And guess what? That's exactly what the answer is. I wrote the answers to make sure that I'm right here. So 2NH3. So again, we had 2 nonmetals. We referred back to our notes. What pattern is that? We're just going to put those 2 together and figure out the bonding, right? We had to go to those valence electrons. You could use the periodic table to do that and figure out how many hydrogens could bond with 1 nitrogen. Okay, second example here, we have silver oxide. So does this look like it's going to be a synthesis reaction or a decomposition? Decomposition, right? We have 1 giant product or 1 giant reactant that we're going to be breaking apart. Great. So now we want to see, well, what do we have? It looks like we have a metal and an oxide or an oxygen. So in this case, we want to go back to our notes. When we had a metal and an oxygen, does it fit any of these situations? Let's see. It definitely doesn't fit an acid. It doesn't have a hydroxide, doesn't have a chlorate or a carbonate. So this one must be a binary compound, meaning it just breaks apart into its separate elements. So if that's true, then we're going to end up getting silver plus oxygen, right? And oxygen, of course, always is going to bind with itself to fill those valence requirements. It will double bond there. And then if we want to do our full work here, we have to balance our equation. So it looks like on this side, we actually have 2 oxygens. That's good. We have 4 silvers. So we're going to want to put a 4 in front of our silver. And even though my 4 looks a little weird there, we have a full balanced equation. Okay, so 3 and 4, you guys are going to try, and then we're going to go over. So again, use the notes, right? Say, okay, what do I have? I have a metal, I have a non-metal, I have an oxide. What do I have? Is number 3 a synthesis? Great question. Yes, right? And again, you could have asked yourself too, could it be single replacement? Well, not really, because what would it replace, right? I just see 2 separate elements there. So great, number 3 is a synthesis. In fact, we'll start going over that one. So it is a synthesis. We're going to go back into those notes and look, what kind of synthesis is it? Well, I saw a hydrogen and a chlorine, which to me is 2 nonmetals. So looks like we're just going to be putting them together again, pretty easy. And remember, guys, if you can't remember if something's a metal or not, right, don't even worry about it. Just go to the periodic table, and guess what? Everything's on here is color coordinated, metals and nonmetals. Find it on the periodic table. Chlorine, nonmetal, okay, and hydrogen, which is gray, it's nonmetal, even though it doesn't really say that explicitly, but it's nonmetal. So we have 2 nonmetals. Okay, so what's hard about this reaction stuff, as we're doing this, you might have noticed, is that it's sort of synthesizing all of the stuff we've learned, right? Using the periodic table, identifying metals versus nonmetals, finding those valence electrons, putting bonding together, balancing an equation, right? And now we're using all of that, plus we're predicting what kind of reaction is going to take place. So this is literally using almost everything we've learned. The only way that we could really incorporate that is if I asked you to find the moles or the number of atoms of something, which we'll get to eventually. So anyway, back to this synthesis equation here, we have hydrogen and chlorine. They're going to bond together. Well, hydrogen has 1 valence electron, chlorine has 7, so they bond together nice and easily, HCl. And in order to balance that out, right, we have 2 of them on the left side, so we need 2 of them on the right side, and that should have been what you got for number 3, 2 HCl. Number 4, hopefully we recognized that's decomposition. What did you guys get for number 4? Keep in mind, use the notes, right? It's decomposition. So we go back to our decomposition slide, or in your case notes, and we look for the pattern. We have a lithium and a hydroxide. We have a metal and a hydroxide, right? We have LiOH. So that means we're going to get a metal with an oxygen and water. Okay. So our metal is lithium with an oxygen. We'll come back and do the bonding in a second. Plus we're going to get water. So what is the bonding going to look like on our lithium and our oxygen? Anyone have any ideas? Ratio of lithiums to oxygens here. Keep in mind lithium has a valence electron of 1. Oxygen has a valence electron of 6. So we're going to need 2 lithiums for every oxygen. Okay, good. So you should have gotten lithium oxide plus water. And if we look for balancing here, I see 2 oxygens, 2 hydrogens, 2 lithiums. On this side, I see 2 lithiums, 2 oxygens, 2 hydrogens. So that one is balanced. So then there we go. That is our decomposition reaction of lithium hydroxide. We get lithium oxide and water. Okay. So here is what I'm going to suggest for you guys to do is in Canvas, in this lesson called Synthesis and Decomposition, right? I went through all these different examples. You might want to look at more. You might want to read about it. You don't have to. You should have enough knowledge to be able to do this. You're going to want to do the practice. So we did 1, 2, 3, 4. We did the first 4. You're probably going to want to try 5, 6, and 7, and then you can check your answers, right? But again, use the examples to see the pattern, right? Because it produces a pattern, and that's what's nice. There is also a virtual session exit ticket. You are going to be identifying if the reaction is synthesis or decomposition, and then predicting the products for these two situations. Those are two from the examples, right? Include the code word for full credit. I'm going to put the code word into the chat right now. So in theory, you should be including the code word if you're answering the question correctly, but specify that it's a code word, please. And yeah, that shouldn't take you too long. So I would do that right now while it's fresh in your mind. You might then want to go back and practice in the lesson some more. I believe it is a quiz assignment that goes with this lesson as well. Okay. So any questions about synthesis decomposition? I would also take a second now to go back while it's fresh in your mind and add in a description of decomposition and an example, or maybe all your examples. We have one type of reaction left, that's combustion, right? So that will be the next type of reaction that we talk about. So if you have any questions, pop them in the chat. Otherwise, we are finished with this virtual session. Hopefully that kind of helped you wrap your head around, at least now we have 4 reactions down and 1 to go. Okay, so I don't see anyone asking a question. So I will assume we have no questions. If you do have a question, right, feel free to email me and let me know. It could be about the exit, it could be about the quiz, whatever. I like what one of the students in the class does. If she gets something wrong and she can't figure it out, she just emails me and says, hey, can you explain why question 3 is this? Right, so that she can continue to learn. So make sure you're looking at the ones you get wrong, and if you can't figure out why you got it wrong, ask me, right? Because sometimes there's errors on the questions even, which we find that way too. All right, so have a good break, everyone. I will see you guys in January. Bye.